Mom, can you buy me new clothes?
I'm sorry, son, but we need to save money for your tuition fees first.
I know, it's just that I'm going to college next month and I only have those things.
Son, I've seen you wear these two shirts with this pair of pants. And you only wear this shirt with this other pair of pants.
That's why I need new clothes. I only have 3 outfits.
Why don't you try mixing up your clothes some more? I'll bet you'll end up with more than 3 outfits.
But
Don't worry, the church is holding a rummage sale in 2 weeks. I'll try to get you some more clothes then.
thanks, Mom.
Ma'am, please don't stop the video. I want to know what will happen to that guy.
You really do like soap operas.
Don't worry, we'll see more of them later. For now, let's consider the son's dilemma. Remember, he has 3 shirts and 2 pairs of pants. How many outfits do you think he can assemble out of these pieces of clothing?
That will require a considerable amount of brain power.
Well, these should help.
Oh wow, let's have a fashion show.
You read my mind, Gabes.
Huh? Is it time for home economics already?
No, you're still in math class, Alvin. Don't worry, there's some math in this.
In that case, I volunteer to be the fashion model.
We need a fashion designer.
I'll be the fashion designer.
Okay, you may now step out of the room and get ready. Remember, each outfit should be unique. Now the rest of us will take note of each outfit that appears. Take note of what clothes make up each outfit and count how many unique outfits they can come up with.
Yes, ma'am!
Okay, we're waiting. Good work, children. Now everyone settle down. So how many outfits can we assemble using 3 shirts and 2 pairs of pants?
6!
That's right, Chris. How did you assemble those outfits?
Well, ma'am, I started out with 1 pair of pants and matched each shirt to it. Then I took the other pair and matched each shirt to it as well.
Let's make a diagram to illustrate what Chris did. He started out with the pants. And how many choices did he have?
2!
Right. That's 1 blue and 1 khaki. According to Chris, he took 1 pair and matched each shirt to it. How many shirt options did he have?
3!
So, that's 3 shirts per pair of pants. 1 blue, 1 yellow, and 1 red. Notice that each path consists of 1 unique outfit. And how many unique outfits are there?
I know there are 6 unique paths, so there are 6 unique outfits.
That's right, Bianca. What we have just constructed is a tree diagram. we can use such a diagram to solve problems like the last one. For example, consider the following menu in a canteen. If a meal were to consist of one type of rice, one viand, and one dessert, in how many ways can we order a meal?
Ma'am, I don't know the answer yet, but I could make a tree diagram.
Go ahead.
Oh, there are 12 pathways. That means there are 12 ways we can order a meal.
Excellent work, Christine. Notice that as we are faced with more options, we end up with larger diagrams.
There must be an easier way, ma'am.
Actually, there is. Look at the 3 diagrams we made. Take note of the total number of paths and the number of options at each stage. Notice anything?
Oh, I see. Ma'am, can I go to the board and point them out?
Sure.
Here in the first diagram, we have 2 options for pants and 3 options for shirts. The product of these options is 6, which is exactly the number of pathways in this diagram. In the second diagram, we have 2 options for rice, 3 options for viands, and 2 options for desserts. So the product of 2, 3, and 2 is 12, which is again the total number of pathways in this diagram.
Wow, I didn't notice that.
Excellent work, Alvin. What you have just uncovered is the fundamental counting principle. This principle states that the number of ways of making several decisions in succession is equal to the product of the number of choices that can be made at each decision. For example, I plan to travel from Manila to Cebu via Legazpi. From Manila to Legazpi, I can go by plane, bus, or train. From Legazpi to Cebu, I can go via plane or boat. In how many ways can I travel from Manila to Cebu via Legazpi?
That's easy, ma'am. You have 3 ways to get from Manila to Legazpi, and you have 2 ways to get from Legazpi to Cebu. So you have 3 times 2, or 6 ways to travel from Manila to Cebu via Legazpi.
You got it, Christine. I have a surprise for you.
What is it, ma'am?
We're going to see more of that boy who's going to college. Yes! Let's see if we can find more problems where we can apply the fundamental counting principle.
Drop it! You know you're not supposed to play with Dad's mug collection. You might break them. Do you remember how these mugs were arranged? Now run along and play with something else.
you trying to be an interior decorator?
No, Mom. Jopet was playing with them. I'm trying to return these mugs in their proper places. I was wondering,
What is it?
maybe I shouldn't go to college and just find work to help out.
Son, you know your father and I would do anything to get you through college and find a decent job.
I could go back to school after I've earned enough for tuition.
No, and that's the end of this discussion. I think we should go.
Is dinner ready?
Your father's home.
Mom,
Yes, son?
I know I act like a brat from time to time, but I really do appreciate what you and Dad have to go through to get Jopet and me through school.
I know. Study hard and we'll take care of the rest.
I would quit school and work if my family fell on hard times.
The mother should get a job.
That would be hard considering her age.
Or the boy could work while studying. That's what I did.
Really, ma'am?
Really, but I wouldn't recommend it. Anyway, did you see anything in the video where we can apply the fundamental counting principle?
Well, there were those mugs. We can find out how many distinct arrangements he can make out of 4 mugs. But I don't see how the principle applies.
We'll get to that, but first, let's solve this problem via brute force.
Brute force?
It means we solve the problem by actually arranging the mugs and finding out how many distinct arrangements we can make. Here, these should help. Come forward and rearrange these mugs and write on the board each arrangement you made. Find out how many different arrangements are possible.
Ma'am, we ended up with 24 unique arrangements.
Good work!
That boy is in trouble. There's only one correct arrangement out of 24 possible arrangements.
Yes, he's got 1 chance out of 24 of getting the right arrangement. Ma'am, using brute force is hard.
True. Fortunately, the fundamental counting principle can be applied in this case. Consider 4 spots on the table as possible locations for the 4 mugs. In the first location, how many options do we have?
We can place one of the 4 mugs there, so we have 4 options.
Right. Now that we have 1 in place, how many options do we have for the second location?
We have 3 mugs left, so we have 3 options for the second location. Oh, I get it. In the third location, we'll have 2 options and only 1 option for the fourth or last location.
You got it. What we did was make several decisions in succession according to the fundamental counting principle. The number of ways of making several decisions in succession is equal to the product of the number of choices that can be made at each decision.
Oh, so now we multiply all these and end up with a number of unique arrangements for 4 mugs. Let's see. 4 times 3 times 2 times 1, that's equal to 24. Hey, that's what we got using brute force.
Another way of writing 4 times 3 times 2 times 1 is this.
Ma'am, how do you read that?
I think it's 4.
Actually, it's read as 4 factorial.
Oh,
Actually, the product of any whole number n and all whole numbers less than it is n factorial. This means n factorial is equal to n times n minus 1 times n minus 2 down to 3 times 2 times 1.
So, 10 factorial is 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1.
Yes, and what is 10 factorial equal to?
That'll be 3,628,800.
Good. Let's write that down. 10 factorial is equal to 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, which is equal to 3,628,800. Now, how about 7 factorial? What is this equal to?
May I, ma'am?
Go ahead, Gabes.
Let's see. N factorial is equal to n times n minus 1 times n minus 2 and so on down to 3 times 2 times 1. That means 7 factorial is equal to 7 times 7 minus 1 or 6 times 7 minus 2 or 5 and so on until 1. Now, multiplying all these factors give us 5,040.
Good job. Now, how about 0 factorial?
Now that's a trick question.
Think of it this way. N factorial is a number of distinct arrangements of n objects. So 0 factorial is a number of distinct arrangements of 0 objects. So how many arrangements do we have?
I give up.
You have one arrangement, an arrangement with no objects.
Oh, so 0 factorial is equal to 1.
Yes. Now here's something which will help us later in the discussion. Consider this problem. Five factorial divided by 3 factorial. If you remember, 5 factorial is 5 times 4 times 3 times 2 times 1. But 3 times 2 times 1 is 3 factorial. So, we are left with 5 times 4, which is 20.
That's a neat trick. Let me try one, ma'am.
Okay, try this. 10 factorial divided by 8 factorial.
So, 10 factorial is equal to 10 times 9 times 8 factorial. 8 factorial over 8 factorial is 1. So we're left with 10 times 9, which is 90.
Good job! Now how about 7 factorial divided by 6 factorial?
May I, ma'am?
Go ahead, Christine.
Seven factorial is equal to 7 times 6. Oops, I can stop on 6. So, 7 times 6 factorial divided by 6 factorial. We're left with 7.
Great. Now let's go back to the mugs. Each distinct arrangement is called a permutation. A permutation is any of the different arrangements of a set of objects. So in our previous problem, we had 24 permutations. Now what if we only have 2 places or slots for 4 mugs? How many distinct arrangements or permutations can we make?
I know, since we only have 2 slots, I'll make 2 blanks. So we have 4 choices for the first spot. And after filling that slot, we are left with 3 choices for the second slot. So we have 4 times 3 or equal to 12 permutations.
Let's see. Can someone come to the board and write down all possible arrangements of the 4 mugs using only 2 slots?
I'll do it. You were right, Gabes. There were 12 permutations.
Both of you did a great job. In that last problem, we found the number of distinct arrangements of 4 objects using only 2 slots. In mathematical terms, that's a permutation of 4 objects taken 2 at a time. In mathematical symbols, it's written like this. In general, sub n, p sub r means a permutation of n objects taken r at a time. Or in layman's terms, the number of distinct arrangements of n objects using only r slots.
Ma'am, does this mean that R should be less than N? After all, you can't take 6 objects from 5.
But you can take 5 objects from 5, or the whole lot.
Oh, so R is less than or equal to N.
That's right. If you'll notice, in the original mug problem, we arranged 4 objects using 4 slots to find the number of permutations of 4 objects taken 4 at a time. In symbols, that's... And we found this to be or 4 factorial or 24. I'd like you to find these other permutations. Well, except for this. We know this to be 4 times 3 or 12.
I'll take the first, I'll take the second.
Good work. Now, what about the last one?
That looks complicated.
No, it's not. Chris, you should know this.
Oh, I remember. That's like arranging 0 objects, so that's 1.
Excellent. Now, class, I'd like you to take a look at the last factor in each permutation except the last one. These can be found using n, the number of objects, and r, the number of slots.
Really?
I know. If I subtract 4 from 4, then add 1, the last factor, 1. I can do the same for the rest. This means the last factor is n minus r plus 1.
Brilliant! So in general, the number of permutations of n objects taken r at a time is equal to n times n minus 1 times n minus 2 down to n minus r plus 1. For example, in how many ways can I seat 8 students in a row if I only have 5 chairs?
Ma'am, isn't that the same as finding the permutation of 8 objects taken 5 at a time?
Yes, it is. Would you like to come to the board and show us exactly how many permutations there are?
Okay. We're looking for the permutation of 8 objects taken 5 at a time. This implies that n is equal to 8 and r is equal to 5. The last factor should be n minus r plus 1, which is in this case equal to 4. So we start writing down the factors from n to 4. That's 8p5 is equal to 8 times 7 times 6 times 5 times 4, all equal to 6,720.
Excellent!
Ma'am, I noticed that the formula works just as well as the method we used a while ago.
What do you mean by that, Bianca?
Well, what we have are 8 objects being arranged in 5 slots. In the first slot, we have 8 options. Once placed, we only have 7 on the second, and so on. We ended up with the same factors.
Yes, it works just as well. That means either method will do. Let's try another problem, but this time, try both methods. In how many ways can I plug in 5 bulbs in a string of Christmas lights with 5 sockets?
I'll solve that one, ma'am.
Go ahead, Alvin.
That's the same as finding the permutation of 5 objects taken 5 at a time. That means we have 5 slots to arrange 5 objects. So in the first slot, we have 5 options. Then 4, then 3, then 2, then 1. That means 5 factorial. That means there are 120 ways.
Very good. Now try the formula.
Okay, in the problem n equals 5 and r equals 5, this means the last factor will be 5 minus 5 plus 1, or simply 1. So the factors will start with 5 down to 1. It's just the same.
Before I go on, let's first consider n minus r factorial. What does this mean?
I know. It's equal to n minus r times n minus r minus 1 times n minus r minus 2 down to 3 times 2 times 1.
Very good. Next, consider the permutation formula. If we would further multiply it down to 1, what will be the next factors?
I know.
Okay, so the next factor is n minus r plus 1 minus 1, or simply n minus r. Next is n minus r minus 1, followed by n minus r minus 2, so on down to 3 times 2 times 1. Wait a minute, this is also equal to n factorial.
I'm glad you noticed. Notice too that this part is a number of permutations of n objects taken r at a time, and this part is n minus r factorial. This means that sub n p sub r times n minus r factorial is equal to n factorial. So if we multiply our original formula for the permutation of n objects taken r at a time by n minus r factorial over n minus r factorial, we end up with the alternative formula for the permutation of n objects taken r at a time. Thus, an alternative formula for the number of permutations of n objects taken r at a time is n factorial over n minus r factorial.
Ma'am, can we apply this version of the formula to our previous problems?
I thought you'd never ask. Let's try the seating problem. In how many ways can I seat 8 students in a row if I only have 5 chairs? Christine?
The problem is the same as permutation of 8 objects taken 5 at a time. Based on the formula, the numerator is 8 factorial and the denominator will be 8 minus 5 factorial. Since 8 factorial is equal to 8 times 7 times 6 times 5 times 4 times 3 factorial, we'll be left with 8 times 7 times 6 times 5 times 4, which is 6,720, which is what we got a while ago.
That's great, Christine. Now, what if 2 of the 5 chairs were broken?
That leaves us with 3 chairs.
So in how many ways can I seat 8 students in a row if I only have 3 chairs?
I'll do it. The problem is the same as the permutation of 8 objects taken 3 at a time. That means the numerator will be 8 factorial and the denominator will be 8 minus 3 factorial. We can cancel 5 factorial from 8 factorial, leaving us with 8 times 7 times 6 or 336.
Excellent, Bianca.
I never thought counting would be that interesting.
Remember, we used a tree diagram to represent a counting problem.
And we used the fundamental counting principle to find the permutations of objects.
And who could forget factorial notation?
Hey, Iggy is here.
You missed math, Iggy.
I had to go to the dentist.
Can you read this?
Of course, that's 4.